Okay, so in order to determine the size of a DNA fragment on a gel, the first thing you have to do is to actually measure from a starting point, which if you look at lane 9 over here, to the edge of the gel. You could just use the edge of this picture if you wanted to. You can kind of see the wells. I'll circle one right over here in orange. You can actually see a well right there. So it just really, you need a common starting point. So I'm just going to use in lane 9, I'm just going to use this edge there. So this control loaded in lane 1 and loaded in lane 9 is lambda DNA digested with the enzyme ND3. Okay, so basically when you start at the beginning of that lane and you measure from that point to the leading edge of each band, that distance, you'll plot that versus base pairs. Now, for each band, you always go back to the start, and you go back to that, measure down to the leading edge of the next band, and so forth, back to the leading edge, down to the next band, right? And you keep measuring every single one. Okay, so the first step, so I guess in the steps in the process, the first step would be measure in millimeters the bands in the control lane. And since we know the size of those in the control, then you can use that. Now you can see that there's, if you look at lane 1, I'll try to erase my marks on lane 1 and clear that up so you can see. Now lane 1, I should erase all of my previous marks so you can follow what I'm talking about. So if you look at lane 1, there's a band down here. That band there is 564 base pairs long. These two bands here, it's this lowest band is 2027 base pairs. The one right above it is 2322 base pairs, and then and so forth. So basically, each one of these bands represents a known. Now, if you're going to try to estimate a band size, so let's just say that you wanted to figure out how big that band was. Since you have a band, you have bands ranging from 2003 down to 564. That means that your graph, if you were to graph that, in this case, base pairs versus millimeters. Okay, since the longer the base pairs, the slower it moves. Okay, so basically, if the base pairs were higher, the slope of your control graph will look like that. So you basically go over there and say, oh, okay, if that one moved this far, I would go up, hit the line, and come over, and that tells me how many base pairs. Well, that's the same thing as using the equation of that line. Okay, so once you get the equation of the line, so y equals mx plus b, if you know, for instance, this is the x-axis, if you know x, these numbers will already be filled in your graph, you can calculate y. And that's really what all graphing software actually does. So once you do let me erase all this again. So once you get the first step where you measure your control, your second step will be to generate a graph of that control. Okay. So when you do that, then you plot the points and then you measure the bands in your unknown. So what I want you to do in this exercise is I actually have this actual picture on a practice exercise. I've actually added some more bands, but what you can do is you can go and say, all right, I want you to graph the control lane, either this one or this one, but you don't have to do both. Graph one of those, make a graph. Once you plot the graph, this would be base pairs on your y-axis and millimeters on your x-axis. And I'll give you a table showing you the links of each of those control lanes. Once you get that graph, then pick your unknown lane. Let's say you're going to determine the base pair of lane 6. You measure from that same starting point, wherever you started in your control lane, measure down to that leading edge of that band, and then plot it. So once you have your graph of either lane 1 or lane 9, then you're just going to use the equation of the line to determine the unknown base pairs. Okay? So that gives you the starting point, and you should be good to go.